In mathematics, a continued fraction is an expression obtained through an iterative process of representing a number as the sum of its integer part and the reciprocal of another number, then writing this other number as the sum of its integer part and another reciprocal, and so on. In a finite continued fraction, the iteration recursion is terminated after finitely many steps by using an integer in lieu of another continued fraction. In contrast, an infinite continued fraction is an infinite expression. In either case, all integers in the sequence, other than the first, must be positive. The integers are called the coefficients or terms of the continued fraction. Continued fractions have a number of remarkable properties related to the Euclidean algorithm for integers or real numbers. Every rational number pq has two closely related expressions as a finite continued fraction, whose coefficients I can be determined by applying the Euclidean algorithm to. The numerical value of an infinite continued fraction will be irrational. It is defined from its infinite sequence of integers as the limit of a sequence of values for finite continued fractions. Each finite continued fraction of the sequence is obtained by using a finite prefix of the infinite continued fractions defining sequence of integers. Moreover, every irrational number I plus or minus is the value of a unique infinite continued fraction, whose coefficients can be found using the non-terminating version of the Euclidean algorithm applied to the incommensurable values I plus or minus and 1. This way of expressing real numbers is called their continued fraction representation. It is generally assumed that the numerator of all of the fractions is 1. If arbitrary values and/or functions are used in place of one or more of the numerators or the integers in the denominators, the resulting expression is a generalized continued fraction. When it is necessary to distinguish the first form from generalized continued fractions, the former may be called a simple or regular continued fraction, or said to be in canonical form. The term continued fraction may also refer to representations of rational functions, arising in their analytic theory. For this use of the term see Parda copyright approximation and Chebyshev rational functions. Motivation and notation. Consider a typical rational number 415/93, which is around 4.4624. As a first approximation, start with 4, which is the integer part. 415/93 equals 4 plus 43/93. Note that the fractional part is the reciprocal of 93/43, which is about 2.1628. Use the integer part, 2, as an approximation for the reciprocal, to get a second approximation of 4 plus 1/2 equals 4.5. 93/43 equals 2 plus 7/43. The remaining fractional part, 7/43, is the reciprocal of 43/7, and 43/7 is around 6.1429. Use 6 as an approximation for this to get 2 plus 1/6 as an approximation for 93/43 and 4 plus 1/2 plus 1/6 euro, about 4.4615, as the third approximation. 43/7 equals 6 plus 1/7 euro. Finally, the fractional part, 1/7, is the reciprocal of 7, so its approximation in this scheme, 7, is exact and produces the exact expression 4 plus 1/2 plus 1/6 plus for 415/93. This expression is called the continued fraction representation of the number. Dropping some of the less essential parts of the expression 4 plus 1/2 plus 1/6 plus gives the abbreviated notation 415/93 equals 4, 2, 6, 7. Note that it is customary to replace only the first comma by a semicolon. Some older textbooks use all commas in the tuple, for example, 4, 2, 6, 7. If the starting number is rational, then this process exactly parallels the Euclidean algorithm. In particular, it must terminate and produce a finite continued fraction representation of the number. If the starting number is irrational, then the process continues indefinitely. This produces a sequence of approximations, all of which are rational numbers, and these converge to the starting number as a limit. This is the continued fraction representation of the number. Examples of continued fraction representations of irrational numbers are, sh19 equals 4, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, a euro. The pattern repeats indefinitely with a period of 6. E equals 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, a euro. The pattern repeats indefinitely with a period of 3 except that 2 is added to one of the terms in each cycle. A euro equals 3, 7, 15, 1292, 1, 1, 1, 2, 1, 3, 1, a euro. The terms in this representation are apparently random. I equals 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, a euro. The golden ratio, the most difficult irrational number to approximate rationally. C. A property of the golden ratio I. Continued fractions are, in some ways, more mathematically natural representations of a real number than other representations such as decimal representations, and they have several desirable properties. The continued fraction representation for a rational number is finite and only rational numbers have finite representations. In contrast, the decimal representation of a rational number may be finite, for example 137 1600ths equals 0.085625, or infinite with a repeating cycle, for example 4/27ths equals 0.148148148148148 a euro. Every rational number has an essentially unique continued fraction representation. Each rational can be represented in exactly two ways, since AO A1, a euro ANA 1, and equals AO A1, a euro ANA 1, ANA 1, 1. Usually the first, shorter one is chosen as the canonical representation. The continued fraction representation of an irrational number is unique. The real numbers whose continued fraction eventually repeats are precisely the quadratic irrationals. For example, the repeating continued fraction, 1, 1, 1, 1, a euro is the golden ratio, and the repeating continued fraction, 1, 2, 2, 2, a euro is the square root of 2. In contrast, the decimal representations of quadratic irrationals are apparently random. The square roots of all integers, that are not perfect squares, are quadratic irrationals, hence are unique periodic continued fractions. The successive approximations generated in finding the continued fraction representation of a number, that is by truncating the continued fraction representation, are in a certain sense the best possible. Basic formula: a continued fraction is an expression of the form where I and b are either rational numbers, real numbers, or complex numbers. If b equals 1 for all I, the expression is called a simple continued fraction. If the expression contains a finite number of terms, it is called a finite continued fraction. If the expression contains an infinite number of terms, it is called an infinite continued fraction. Thus, all of the following illustrate valid finite simple continued fractions. Calculating continued fraction representations, consider a real number r. Let I equals r be the integer part of r and let f equals I be the fractional part of r. Then the continued fraction representation of r is I. A1, A2, a euro, where A1, A2, a euro is the continued fraction representation of 1 per Fahrenheit. To calculate a continued fraction representation of a number r, write down the integer part of r. Subtract this integer part from r. If the difference is 0, stop. Otherwise find the reciprocal of the difference and repeat. The procedure will halt if and only if r is rational. This process can be efficiently implemented using the Euclidean algorithm when the number is rational. The number 3.245 can also be represented by the continued fraction expansion, 3, 4, 12, 3, 1. Refer to finite continued fractions below. Notations for continued fractions: the integers a0, a1 etc., are called the coefficients or terms of the continued fraction. One can abbreviate the continued fraction in the notation of Carl Friedrich Gauss, or as or in the notation of Pringham as, or in another related notation as. Sometimes angle brackets are used, like this. The semicolon in the square and angle bracket notations are sometimes replaced by a comma. One may also define infinite simple continued fractions as limits. This limit exists for any choice of AO and positive integers A1, A2. Finite continued fractions. Every finite continued fraction represents a rational number, and every rational number can be represented in precisely two different ways as a finite continued fraction, with the conditions that the first coefficient is an integer and other coefficients being positive integers. These two representations agree except in their final terms. In the longer representation, the final term in the continued fraction is 1. The shorter representation drops the final 1, but increases the new final term by 1. The final element in the short representation is therefore always greater than 1, if present. In symbols, AO, A1, A2, a euro, and A1, an 1, equals, AO. A1, A2, a euro, and A1, and plus 1. AO. 1, equals, AO plus 1. For example, 2.25 equals 2 plus 1 quarter equals, 2. 4, equals 2 plus 1 third plus 1 first equals, 2. 3, 1, a 4.2 equals a 5 plus 4 fifths equals a 5 plus 1 first plus 1 quarter equals, a 5. 1, 4, equals a 5 plus 1 first plus 1 third plus 1 first equals, a 5. 1, 3, 1. Continued fractions of reciprocals. The continued fraction representations of a positive rational number and its reciprocal are identical except for a shift one place left or right depending on whether the number is less than or greater than 1 respectively. In other words, the numbers represented by AO, A1, A2, a euro, and 0. AO, A1, a euro, and are reciprocals. This is because if A is an integer then if x1 then x equals a plus 1 slash b and 1 slash x equals 0 plus 1 per a plus 1 slash b, with the last number that generates the remainder of the continued fraction being the same for both x and its reciprocal. For example, 2.25 equals 9 quarters equals, 2. 4, 1 slash 2.25 equals 4 ninths equals, 0. 2, 4. Infinite continued fractions. Every infinite continued fraction is irrational, and every irrational number can be represented in precisely one way as an infinite continued fraction. An infinite continued fraction representation for an irrational number is useful because its initial segments provide rational approximations to the number. These rational numbers are called the convergence of the continued fraction. The larger a term is in the continued fraction, the closer the corresponding convergent is to the irrational number being approximated. Numbers like I euro have occasional large terms in their continued fraction, which makes them easy to approximate with rational numbers. Other numbers like E have only small terms early in their continued fraction, which makes them more difficult to approximate rationally. The golden ratio A has terms equal to 1 ever you hear a euro, the smallest values possible a euro, which makes I the most difficult number to approximate rationally. In this sense, therefore, it is the most irrational of all irrational numbers. Even-numbered convergents are smaller than the original number, while odd-numbered ones are larger. For a continued fraction, AO, A1, A2, a euro, the first four convergents are AO/1, A1 AO plus 1 per A1, A2, A1 AO plus 1, plus AO per A2 A1 plus 1, A3, A2, A1 AO plus 1, plus AO, plus slash A3, A2 A1 plus 1, plus A1. In words, the numerator of the third convergent is formed by multiplying the numerator of the second convergent by the third quotient, and adding the numerator of the first convergent. The denominators are formed similarly. Therefore, each convergent can be expressed explicitly in terms of the continued fraction as the ratio of certain multivariate polynomials called continuants. If successive convergents are found, with numerators h1, h2, a euro and denominators k1, k2, a euro, then the relevant recursive relation is hn equals an hn a 1 plus hn a 2, kn equals an kn a 1 plus kn a 2. The successive convergents are given by the formula, hn kn equals an hn a 1 plus hn a 2 slash an kn a 1 plus kn a 2, thus to incorporate a new term into a rational approximation, only the two previous convergents are necessary. The initial convergents are 0 a 1 and 1 a 0. For example, here are the convergents for 0, 1, 5, 2, 2. When using the Babylonian method to generate successive approximations to the square root of an integer, if one starts with the lowest integer as first approximant, the rationals generated all appear in the list of convergents for the continued fraction. Specifically, the approximants will appear on the convergence list in positions 0, a euro 1, a euro 3, a euro 7, a euro 15, a euro, a euro 2 car 1. For example, the continued fraction expansion for ℏ3 is 1, 1, 2, 1, 2, 1, 2, 1, 2, a euro. Comparing the convergence with the approximants derived from the Babylonian method. x0 equals 1 first, x1 equals 1 half, 1 plus 3 firsts, equals 2 firsts equals 2, x2 equals 1 half, 2 plus 3 halves, equals 7 quarters, x3 equals 14 plus 34, equals 97/56. Properties of infinite continued fractions. Bayer space is a topological space on infinite sequences of natural numbers. The infinite continued fraction provides a homeomorphism from Bayer space to the real numbers. The infinite continued fraction also provides a map between the quadratic irrationals and the dyadic rationals, and from other irrationals to the set of infinite strings of binary numbers. This map is called the Minkowski question-mark function. The mapping has interesting self-similar fractal properties. These are given by the modular group, which is the subgroup of Mobius transformations having integer values in the transform. Roughly speaking, continued fraction convergence can be taken to be Mobius transformations acting on the upper half plane. This is what leads to the fractal self-symmetry. Some useful theorems: if A0, A1, A2, a euro is an infinite sequence of positive integers, define the sequences Hn and Kn recursively. Theorem 1. For any positive real number z. Theorem 2. The convergence of A0, A1, A2, a euro are given by. Theorem 3. If the nth convergent to a continued fraction is Hn Kn, then Corollary 1, each convergent is in its lowest terms. Corollary 2, the difference between successive convergents is a fraction whose numerator is unity. Corollary 3, the continued fraction is equivalent to a series of alternating terms. Corollary 4, the matrix has determinant plus or minus 1, and thus belongs to the group of 2A, 2 unimodular matrices GL, 2, Z. Theorem 4. Each convergent is nearer to a subsequent convergent than any preceding convergent is. In symbols, if the nth convergent is taken to be A0, A1, n equals xn, then for all R0, that is closer to x than any approximation with a smaller or equal denominator. The simple continued fraction for x generates all of the best rational approximations for x according to three rules: truncate the continued fraction, and possibly reduce its last term. The reduced term cannot have less than half its original value. If the final term is even, half its value is admissible only if the corresponding semi-convergent is better than the previous convergent. For example, 0.84375 has continued fraction, 0, 1, 5, 2, 2. Here are all of its best rational approximations. The strictly monotonic increase in the denominators as additional terms are included permits an algorithm to impose a limit either on size of denominator or closeness of approximation. The half rule mentioned above is that when arc is even, the halved term arc/2 is admissible if and only if xa, ao, a1, a euro, arc a1, xa, ao, a1, a euro, arc a1, arc/2, this is equivalent to arc arc A1, a euro, A1, arc. Arc plus 1, a euro. The convergence to X are best approximations in an even stronger sense. ND is a convergent for X if and only if dxAN is the least relative error among all approximations MC with Ca per mole currency D. That is, we have dxANY when K is odd. For example, the number 355/113 has the continued fraction representations, 355 113 equals 3. 7, 15, 1, equals 3. 7, 16, and thus 355/113 is a convergent of any number strictly between. Comparison of continued fractions, consider X equals A0. A1, a euro and Y equals B0. B1, a euro. If K is the smallest index for which arc is unequal to Bk, then X0 are the partial numerators, the Bn are the partial denominators, and the leading term BO is called the integer part of the continued fraction. To illustrate the use of generalized continued fractions, consider the following example. The sequence of partial denominators of the simple continued fraction of I does not show any obvious pattern. However, several generalized continued fractions for I have a perfectly regular structure, such as. The first two of these are special cases of the arctangent function with I equals 4 arctan sh, 1. Other continued fraction expansions. Equals periodic continued fractions equals. The numbers with periodic continued fraction expansion are precisely the irrational solutions of quadratic equations with rational coefficients. Rational solutions have finite continued fraction expansions as previously stated. The simplest examples are the golden ratio I equals 1. 1, 1, 1, 1, 1, a euro and sh 2 equals 1. 2, 2, 2, 2, a euro, while sh 14 equals 3. 1, 2, 1, 6, 1, 2, 1, 6 a euro and sh 42 equals 6. 2, 12, 2, 12, 2, 12 a euro. All irrational square roots of integers have a special form for the period. A symmetrical string, like the empty string or 1, 2, 1, followed by the double of the leading integer. Equals a property of the golden ratio I equals, because the continued fraction expansion for I doesn't use any integers greater than 1, I is one of the most difficult real numbers to approximate with rational numbers. Hurwitz's theorem states that any real number k can be approximated by infinitely many rational mn with. While virtually all real numbers k will eventually have infinitely many convergents mn whose distance from k is significantly smaller than this limit, the convergence for I consistently toe the boundary, keeping a distance of almost exactly away from I, thus never producing an approximation nearly as impressive as, for example, 355/113 for I. It can also be shown that every real number of the form a plus b/c plus d, where a, b, c, and d are integers such that or da bar c equals a plus or minus 1, shares this property with the golden ratio I. And that all other real numbers can be more closely approximated. Equals regular patterns in continued fractions equals, while there is no discernible pattern in the simple continued fraction expansion of I, there is one for e, the base of the natural logarithm, which is a special case of this general expression for positive integer n. Another, more complex pattern appears in this continued fraction expansion for positive odd n, with a special case for n equals 1. Other continued fractions of this sort are where n is a positive integer. Also, for integral n, with a special case for n equals 1. If in x is the modified, or hyperbolic, Bessel function of the first kind, we may define a function on the rationals p cube I, which is defined for all rational numbers, with p and q in lowest terms. Then for all non-negative rationals, we have with similar formulas for negative rationals. In particular we have many of the formulas can be proved using Gauss's continued fraction. Equals typical continued fractions equals, Most irrational numbers do not have any periodic or regular behavior in their continued fraction expansion. Nevertheless, Khinchin proved that for almost all real numbers x, the I have an astonishing property: their geometric mean is a constant independent of the value of x. Paul La copyright v showed that the nth root of the denominator of the nth convergent of the continued fraction expansion of almost all real numbers approaches an asymptotic limit, approximately 3.27582, which is known as La copyright v's constant. Locke's theorem states that nth convergent of the continued fraction expansion of almost all real numbers determines the number to an average accuracy of just over n decimal places. Generalized continued fraction for square roots. Continued fraction techniques are one method of computing square roots. The identity leads via recursion to the generalized continued fraction for any square root. Pell's equation. Continued fractions play an essential role in the solution of Pell's equation. For example, for positive integers p and q, and non-square n, it is true that p2 and q2 equals a plus or minus 1 if and only if pq is a convergent of LSHN. Continued fractions and dynamical systems. Continued fractions also play a role in the study of dynamical systems, where they tie together the Féré fractions which are seen in the Mandelbrot set with Minkowski's question mark function and the modular group gamma. The backwards shift operator for continued fractions is the map h, x, equals 1/xa-1/x, called the Gauss map, which lops off digits of a continued fraction expansion, h, 0. a1, a2, a3, a euro equals 0. a2, a3, a euro. The transfer operator of this map is called the Gauss-Euro-Kuzmin-Euro-Wiersing operator. The distribution of the digits and continued fractions is given by the zeroth eigenvector of this operator, and is called the Gauss-Euro-Kuzmin distribution. Eigenvalues and eigenvectors. The Lanczos algorithm uses a continued fraction expansion to iteratively approximate the eigenvalues and eigenvectors of a large sparse matrix. Examples of rational and irrational numbers. Rational approximant obtained by expanding continued fraction up to r. History of continued fractions. 300 BC Euclid's Elements contains an algorithm for the greatest common divisor which generates a continued fraction as a byproduct. 499 The Arpata contains the solution of indeterminate equations using continued fractions. 1579 Raphael Bombelli, L'algebra opera Euro method for the extraction of square roots which is related to continued fractions. 1613 Pietro Cataldi, Trattato del modo brevissimo di trovare squadra degli numeri Euro first notation for continued fractions. Cataldi represented a continued fraction as AO and N1/D1. And N2/D2. And N3/D3 with the dots indicating where the following fractions went. 1695 John Wallis, Opera Mathematica Euro introduction of the term continued fraction. 1737 Leonhard Euler, De Fraction Ibers Continui Dissertatio Euro provided the first then comprehensive account of the properties of continued fractions, and included the first proof that the number E is irrational. 1748 Euler, Introductio in Analysing Infinitorum. Vol. I, Chapter 18 Euro proved the equivalence of a certain form of continued fraction and a generalized infinite series, proved that every rational number can be written as a finite continued fraction, and proved that the continued fraction of an irrational number is infinite. 1761 Johann Lambert Euro gave the first proof of the irrationality of I Euro using a continued fraction for tan, x. 1768 Joseph Louis Lagrange Euro provided the general solution to Pell's equation using continued fractions similar to Bombelli's. 1770 Lagrange Euro proved that quadratic irrationals expand to periodic continued fractions. 1813 Carl Friedrich Gauss, Worker, Volume 3, pages 134 Euro 138 Euro derived a very general complex-valued continued fraction via a clever identity involving the hypergeometric function. 1892 Henri Parda copyright to find Parda copyright approximant. 1972 Bill Gosper Euro first exact algorithms for continued fraction arithmetic. See also, Sturmy Euro Brocot tree, computing continued fractions of square roots. complete quotient, Engel expansion, generalized continued fraction, mathematical constants, restricted partial quotients, infinite series, infinite product, iterated binary operation, Euler's continued fraction formula, SHLESZYA-Skia-Euro-Prinction theorem, infinite compositions of analytic functions. Notes. References: Seebeck, H. Weber. Periodisch Kettenbruch 1/4 Che. J. Rainanju. Math 33 pages 68-70. Heil Ehrman, J. B. H. Weber. Die Verwandlung von Rayon in Kettenbruch 1/4 Che. J. Rainanju. Math 33 pages 174-188. Magnus, on. Continued fractions associated with the Pada copyright table. Math. ZEITSCHR. 78 pages 361-374. Chen Fan. Xia, Liang San. Continued fraction inversion by Routh's algorithm. IEEE trans. Zec. Theory 16 pages 197-202 doi, 10.1109/TCT. 1969.10829225. Gragg, William B. Matrix Interpretations and Applications of the Continued Fraction Algorithm. Rocky Mount. J. Math 4. Pages 213 doi, 10.1216/RJM 1974-4-2-213. Jones, William B. Thrun, W. J. Continued Fractions, Analytic Theory and Applications. Encyclopedia of Mathematics and its Applications 11. Reading. Massachusetts, Addison Wesley Publishing Company. ISBN 0-201-13510-8. Kinshin, Aya. Originally published in Russian, 1935. Continued Fractions. University of Chicago Press. ISBN 0-486-69630-8. Long, Calvin T., Elementary Introduction to Number Theory, Lexington, D.C. Heath & Company, LCCN 77-171,950, Perrin, Oscar. Die Lieu von den Kettenbruch 1/4 Chen. New York, Chelsea Publishing Company. Pettifrezzo, Anthony J. Pickett, Donald R., Elements of Number Theory, Englewood Cliffs, Prentice Hall, LCCN 77-81766, Rocket, Andrew M. Sa 1/4 S. Peter. Continued Fractions. World Scientific Press. ISBN 981-02-1047-7. H. S. Wall, Analytic Theory of Continued Fractions, Devan Nostran Company, Incorporated, 1948. ISBN 0-8284-0207-8, Cute, A. Breivik Peterson, 5. Bedonk, B. Wardland, H. Jones, W. B. Handbook of Continued Fractions for Special Functions. Springer Verlag. ISBN 978-1-4020-6948-2. Rieger, G. J. A New Approach to the Real Numbers. Ab. Braunschweig-Wies. JIS 33 pages 205-217. External links, Haswinkel, Michiel, ed., Continued Fraction, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, An Introduction to the Continued Fraction, Linus Webster's Continued Fractions and Gaps reviews chaotic structures in continued fractions. Continued fractions on the Sternberg-Cotriot cut the knot, the Antikythera mechanism I, gear ratios and continued fractions, Continued Fraction Calculator, WIMS. Continued Fraction Arithmetic Gosper's first Continued Fractions paper, unpublished. Cached on the Internet Archive's Wayback Machine, Westerstein, Eric W., Continued Fraction, MathWorld. Continued Fractions by Stephen Wolfram and Continued Fraction Approximations of the Tangent Function by Michael Trott, Wolfram Demonstrations Project. A Euroshay 133593 exact continued fraction for pi, a view into fractional interpolation of a continued fraction 1. 1, 1, 1.